For this example, we'll talk a little bit about Usain Bolt, a Jamaican sprinter who is currently the fastest man alive. He has been clocked at speeds of 28 miles per hour. That comes out to be 12.5 meters per second. Assume that during a particular race he's running at 11.7 meters per second and accelerates to his top speed in 1.4 seconds. We'd like to know what is his acceleration during that time and what distance does he cover while he's accelerating. A velocity time graph would look like this, with 11.7 meters per second and 12.5 meters per second and 1.4 seconds. Slope upward like that, starting at 11.7 and ending at 12.5. His initial velocity is 11.7 meters per second. His final speed is 12.5 meters per second. The time it takes him to go from one speed to the other is a short 1.4 seconds. We want to know his acceleration, and we want to know the distance he covers. For part A, I notice that we have two velocities, a time and an acceleration, and we don't know displacement yet. I would go with the first equation, solving for acceleration. So V equals V initial plus AT. I'll go ahead and plug in the numbers and solve it with numbers this time. So 12.5 meters per second equals 11.7 meters per second plus A times 1.4 seconds. To solve, I would need to subtract 11.7 from both sides. 12.5 minus 11.7 is 0.8, as his change of speed equals A times 1.4 seconds. Divide by 1.4. And the acceleration will come out to be 0.8 divided by 1.4. 0.8 divided by 1.4. 0.57 meters per second squared. 0.571 meters per second squared. I get meters per second squared because I have meters here, divide by seconds a second time, giving me seconds squared in the denominator. What distance does he cover to do that? That's part B. And so for part B, I need to find an equation that allows me to solve for distance. The first equation would not be a very good choice this time. The second, this equation would be fine. I know a time, I know an acceleration, I know starting velocities. This equation would be fine. I know two velocities and a time. This equation would be fine. I know two velocities and an acceleration. Let's do this. Let's do the last equation. V squared plus 2a delta x. I'm solving for delta x. I'll go ahead and plug numbers in and solve it, doing it that way this time. So 12.5 meters per second squared equals 11.7 meters per second, quantity squared, plus 2 times a, 0.571 meters over second squared, times delta x. Squaring 12.5, squaring 11.7, and then subtracting those two quantities. 12.5 squared minus 11.7 squared. It's very important you square both numbers before subtracting. I get 19.36. 19.36 meters squared over second squared. 2 times 0.571. I'll divide by 2 and divide by 0.571. Divide by 2 and 0.571. That will cancel out the 2 and the 0.571, leaving me with delta x equals, now all of that, 19.36 divided by 2 divided by 0.571, and I get 16.95 or 17 meters. To find the units, I have meters squared over second squared. The second squareds cancel. One of the meters is canceled. I'm left with meters, which is what I want for distance. And so during this race, he's already traveling very fast. He sprints to his top speed. His acceleration doesn't look like it's very big, but it doesn't take him very long to get there, 1.4 seconds. You'd think with a small acceleration like that, but he covers 17 meters, which is a goodly distance. In a football game, somebody covering 17 meters that'd be considered a very good run during a football game.